All right, let's talk about two words that get thrown around all the time in electrical work: grounding and bonding. They sound similar, but the difference between them is one of the most misunderstood concepts out there. And getting it wrong, well, that can be a deadly mistake. But when you get it right, it's literally a lifesaver. So, to kick things off, let's start with a little quiz, just a gut check. When it comes to keeping a person, you or me, safe from a nasty electric shock, what's more important? Is it the grounding system or is it the bonding system? Have a think.
Okay, let's ask it a different way. Which one of these systems was designed from the very beginning with the number one job of ensuring human safety? What's its primary purpose? And for the last question, let's just flip it on its head. Which system is less about protecting the appliance, the gear itself, and more about protecting the person using it? Okay, you ready? The answer to every single one of those questions is bonding. Now, if you got all three right, that's awesome. You're already ahead of the curve. But if you thought grounding for any of them, don't sweat it. That is a super common mix-up, and we're going to clear it all up right now. So let's really dive in and figure out what these two things actually are. We're going to get to the bottom of why bonding is the true hero when your safety is on the line. Here it is, the big difference. In a nutshell, grounding, that's for your stuff. It's designed to protect your equipment from huge voltage spikes, like a lightning strike. It gives that crazy energy a safe path to the earth. But bonding? Bonding is for you. It's all about protecting people from the most common type of electrical danger, a ground fault. So what is grounding, really? Well, it's exactly what it sounds like. It's the physical connection of your whole electrical system to the planet Earth. You literally drive a big metal rod into the ground and wire it up. All this does is give your system a reference point for 0 volts. Now, bonding is a totally different game. See, it's not about connecting things to the dirt. It's about connecting all the metal things to each other. Think of it like this. You're building a metal superhighway that links the metal casing of your oven, your fridge, your junction boxes, all of it into one continuous network. Okay, theory is great, but to really feel the life or death difference here, let's walk through a scenario that could happen in any kitchen. We're going to look at what happens when an oven goes bad. Before we get to the disaster, though, we need to meet our hero. It's a wire called the Equipment Grounding Conductor, or the EGC. This is the wire that does all the bonding. And, it's a lot like a fire extinguisher. It can sit there for years, decades even, and do absolutely nothing. Until that one day when everything goes wrong and it suddenly becomes the most important thing in the house. Okay, so check this out. Scenario 1, an oven with no bonding. A live wire inside gets freed and touches the metal frame. Now that electricity wants to get back to the source, but its only path is through the ground rod into the earth. Here's the problem. The earth is a really bad conductor. It's got tons of resistance, so only a tiny little trickle of current actually flows, nowhere near enough to trip the circuit breaker. And the result? That entire metal oven is now energized, just sitting there, a silent trap waiting for someone to touch it. Now, let's hit rewind and run that exact same fault, but this time with a proper bonding system in place. The live wire touches the metal frame, but now that frame is connected to our hero, the EGC, that metal superhighway. The electricity doesn't have to struggle through the earth. No way. It has a wide open, low-resistance path right back to the panel. And this causes a massive, insane surge of current that slams the circuit breaker open in a fraction of a second. The power's cut and the danger's gone. Just like that. The difference is just staggering, isn't it? So why? Why is the outcome so completely different? Well, let's look at the actual numbers. Let's see the science that explains why the breaker is a hero in one scenario and, well, a useless bystander in the other. What that bonding wire creates is what the code calls an effective ground fault path. It sounds technical, but it just means we're intentionally giving any stray electricity a really, really easy road home. We're paving the way for it to get back to the panel as fast as possible so it can trip the breaker. So let's put some numbers to it. In our first scenario, without bonding, the current had to go through the earth. A pretty typical resistance for soil is about 25 ohms. On a 230-volt system, that means you only get about 9.2 amps of current flowing. That's it. And here is the terrifying part. Your kitchen outlet is probably on a 20-amp breaker. When that breaker sees 9.2 amps, you know what it does? Nothing. It thinks it's just a heavy load, that everything is perfectly fine. It will not trip. It will happily let that oven stay lethally energized for hours.
But now, look at what happens with our bonded system. That EGC wire, our superhighway, has incredibly low resistance, let's say zero point 0.3 ohms. The same 230-volt fault through that path creates a colossal 767 amps of current. A 20-amp breaker that suddenly sees a 767-amp tidal wave of current doesn't think, it doesn't hesitate, it trips. Instantly. We're talking milliseconds. The circuit is dead, the hazard is neutralized, and a person is saved. That right there is the power of bonding.
And just so we're clear, this isn't just a good idea or an electrician's best practice. This is a non-negotiable life and death requirement that is baked right into the electrical code. And the people who write the rules, they couldn't be clearer. This is from the Philippine Electrical Code, but you'll find similar language everywhere. It says you shall connect things together to create that path. It's not a suggestion. It's not optional. It's a command. So let's just boil this all down. What do you need to remember? First, bonding protects people, grounding protects equipment. Simple as that. Bonding works because it creates that low-resistance superhighway for fault current to travel on. That superhighway allows for a massive surge of electricity, and it's that massive surge that forces your circuit breaker to do its job instantly and save your life. Without bonding, that breaker might as well not even be there during a fault.
So now you know, the difference isn't just a technical detail. It's the difference between a close call and a catastrophe. It really is that simple. So the next time you plug something in, you might find yourself wondering, is this thing just grounded, or is it properly, life-savingly bonded? Thanks for diving into this with me.